So now I want to look at in the same kind of idea of how do we solve higher order differential equations with constant coefficients. So we're going to have an m to the n plus an minus 1 m to the n minus 1 and so forth. This is your auxiliary equation. You'd have this same kind of idea of your auxiliary equation here, and you want to solve this. One solution is they're all distinct real roots, in which case you just have c1 e to the m1x plus c2 e to the m2x and so forth. Again, as a reminder, we are using the fact that y is equal to e to the mx, and that's how we get that auxiliary equation. So you'd have your distinct real roots. If they're all distinct, you get these nice little equations put together. If your m1 has multiplicity of k, then you get a c1 e to the m1x plus c2x e to the m1x, and then plus c3 m squared e to the m1x, and keep going up until you get to the term right before that. So x to the k minus 1, whatever that is. So you just keep going till you get to 1 less than whatever your multiplicity is. And so that's what that would look like if you had that multiplicity. And you can have different combinations of these. So let's go ahead and solve this equation with that. And then we'll look at case 3. So let's go ahead and solve this equation. So the first thing I need to do is get my auxiliary equation. Again, we are using the fact that y is equal to e to the mx. And we're plugging that in. And when we do that, we're going to get m cubed. When you take the third derivative of this, you're going to get an m cubed plus 3m squared minus 4m, then minus 12 equals 0. Again, the reason is we're putting e to the mx in all of these and pulling that out, and that's why it becomes like this. You then solve this equation. Again, you can use technology to do this. I don't care how you go about solving this. And you get the answer, and m turns out to be 2, negative 2, negative 3. So we give a third order equation, quadratic equations. We should get 3 answers. We get 3 distinct answers. So that means my solution is y is equal to c1 e to the 2x plus c2 e to the minus 2x plus c3 e to the minus 3x. And you can use technology or whatever to solve these. Okay, so there's that one. Let's try another one. So we've got y triple prime minus 6y double prime plus 12y prime minus 8y equals 0. Again, we are using the fact that y equals e to the mx. We're plugging that in, finding that when you take the third derivative of this, you will get an m cubed. When you take the second derivative, you get an m squared. When you take the first derivative, you get an m. When you take no derivative, you get no m. Each one of these has an e to the mx in it. We pull that out, and that's where we get our auxiliary equation. So this is my auxiliary equation. You would then find the solution using technology, most likely, or you can solve it by hand. I don't care what you do here. It turns out m equals 2. So it does actually help if you have a technology that will factor it for you so you can see your multiplicity equations. Instead of just finding the solution of this, using technology that just finds it, you want to factor it so you can see your multiplicity. That means that we are supposed to have 3 solutions because this is a third order equation. So this has multiplicity 2. I'm sorry, multiplicity 3, because there's only 1. If there was 2, then one of them would have multiplicity 2, because you need to have 3 solutions to this quadratic polynomial equation. So that means my solution is y is equal to c1 e to the 2x plus c2. And again, if I don't have an x in there, I don't have linearly independent. So that's where that x comes in. Plus c3x squared is always going to be 1 less than your multiplicity. If this was multiplicity 3, we have an x squared. If it was multiplicity 4, we go up to x cubed, e to the 2x. Notice there are 3 solutions, and this third order differential equation should have 3 solutions. All right, Let's do one more. I do want to mention that when we have the complex conjugates with higher order, it gets more complicated to try to generally write it out. So you just have to kind of do the solution and see what you come up with. Let's try this equation. As a reminder, you are letting y equal e to the mx. This means I'm taking the fourth derivative. So if you take the fourth derivative of e to the mx, you're going to get m to the fourth times e to the mx minus 7m squared e to the mx minus 18 e to the mx. Pull that e to the mx out, factor it out, it's gone, equals 0. So now you have this equation to solve. We can now solve this equation. It turns out this equation is m, the solution to this equation is m is plus or minus square root of 2i. And then m equals 3 and m equals negative 3. So there are 4 solutions, 2 complex conjugates, 2 real solutions. So when we go to do this, I usually like to do my real solutions first and then my complex ones. And you just kind of think about it. My real solutions are going to be C1 e to the m, so 3x, plus C2 e to the minus 3x. Those 2 real distinct roots will give me that. There are 2 complex, so I'm also going to have a C3 e to the alpha, but the alpha, the real part of this is 0, so there is no alpha x term, it's 1. So we're going to have C3 cosine of square root of 2x plus C4 sine of square root of 2x. And there's your solution. And they can get more complicated than this. You just want to think about what each piece will give you. If you had 2 roots that had multiplicity, then you'd have to worry about those solutions and how they would go together.